Hi, welcome once again to Mathematics as a Second Language. And today we're going to start a new part of our journey. It's going to be to revisit fractions. And in my mind, fractions is one of the most misunderstood and most frightening part of math. And my feeling is there's no reason for it to be that way. It's part of the chronicle of human endeavor. You remember when we were discussing the development of place value, we mentioned that innovations don't usually take place in a vacuum. Fractions are just one step beyond dealing with whole numbers. And in fact, what happens with fractions is the actual fraction is an abbreviation for two whole number operations. And I thought because this is a refresher course in a sense, in other words, unlike a course where you're teaching chronologically in a classroom, since you've all been exposed to fractions, I feel it's safe to do what we call a flashback. I'm going to start with fraction notation and show you why it's so important to understand whole numbers. What you're going to see if I'm successful is that taking a fractional part of a number involves two whole number operations. And I think the best way to see that is perhaps in terms of how comfortable we are with such an expression as a half an hour. In fact, most people don't even think they're talking about a fraction. You say half hour, and the person almost instinctively thinks of 30 minutes. You say a half a dozen, people think of 6. But somehow or other, if you say 3/5, that's not as common because we don't usually talk about things that come in fifths. So let's look at a half hour from a different point of view. Let's think of this rectangle as representing a whole hour. Another name for a whole hour is 60 minutes. So what is 1/2 of the rectangle? Well, you divide the rectangle into two parts of equal size. And so how big is each part? Well, 60 minutes divided by 2 is 30. And somehow or other, when we talk about 30 minutes, we're not talking about a fraction. It's rather strange that way. If I say to you, it took me 7/60ths of an hour to walk from the parking lot to the TV studio, you might say, well, I'm not comfortable with fractions. But if I say it took me 7 minutes, you say, oh, now I'm more comfortable. Because what you see now as an adjective is a whole number. And what is minute? It's a word that takes the place of saying one of what it takes 60 of to make an hour. See, in other words, minute replaces one of what it takes 60 of to make 1 hour. So in the similar way, what would 1/5 of an hour be? See, you're used to saying, I'll be there in a half hour. You're not that used to saying, I'll be there in 1/5 of an hour. But in the same way that a half hour means you divide the hour into two parts of equal size, 1/5 of an hour means you divide the hour into 5 parts of equal size. So this is still 60 minutes. And how do I divide this into 5 equal parts? Notice I'm talking geometrically, but it's going to be what? The arithmetic step, you take the 60 minutes and divide it by 5. And since 60 divided by 5 is 12, each part is 12 minutes. And what if I wanted 3/5 of an hour? Well, 3/5 is 3 times 1/5. So I'll just take 3 of the 5 pieces. And that's 12, 12, and 12. And what am I doing here? I'm multiplying 12 minutes by 3, and so the answer is 36 minutes. In other words, if you're uncomfortable with 3/5 of an hour, just say 36 minutes. Now, how did we compute 3/5 of an hour? We took the hour, we first divided it by 5, and then we multiplied it by 3. I think that's kind of an amazing thing that people have trouble with fractions in the sense that all it means is to take 3/5 of a number, you divide the number into 5 parts of equal size, and that's why the bottom number, the 5 and 3/5, is called the denominator. It's the denomination. It tells you the size of each piece, and then the numerator, the 3, tells you how many of those pieces you're taking. The 3 is just the adjective. 3/5 is just another adjective noun theme. 3 of what it takes 5 of to make whatever it is that you're talking about. You see, when you start with whole numbers, people thought, okay, this is the smallest unit. You're not going to count half a sheep when you're counting how many sheep you have in your flock. But when it comes to other things, like money, you might want to buy a fractional part of something. You might not want to buy a whole pound. You might not want to measure a whole mile. You might want to measure something shorter. And what happens is, as long as you can use words, you don't have to have fractions. If I want to talk about one of what it takes 24 of to make a whole day, I don't have to say 1/24th of a day. I just say 1 hour. The problem comes up when you can't use the nouns. For example, why would I want to be able to find common multiples of numbers? Well, we already know that 3/5 of an hour is 36 minutes. We just figured that out. Most of us know that 1/4 of an hour or a quarter of an hour is 15 minutes. So if I say to you, how much is a 1/4 of an hour plus 3/5 of an hour, and you don't like fractions, you say, oh, another name for 1/4 of an hour is 15 minutes. Another name for 3/5 of an hour is 36 minutes. Now I have the nouns I like because the adjectives are now whole numbers. So the answer is 15 plus 36. Why can I add them here? Because they're modifying the same noun. Why couldn't I add the 1 and the 3 here? Because the 1 was modifying fourths and the 3 was modifying fifths. I had to find a common denomination, and I was lucky enough that that common denomination was 60, and 60 reminded me of the number of minutes in an hour. So the answer to the problem would be 1/4 of an hour plus 3/5 of an hour is 51 minutes, but 51 minutes is what part of an hour? It's 51 of what it takes 60 of to make an hour. So you begin to see how this is just another language. Now you see, we're not always going to be this fortunate. In this case, we were kind of lucky in the sense that 60 was divisible by both 4 and 5. Not only that, but what if somebody said to us, look, I know that what you did now, if we're dealing with the concept of an hour, but why do we have to be dealing with hours? Maybe we could be dealing with distances. Maybe we could be dealing with cost per pound. What if I just want to know what is 1/4 plus 3/5 without mentioning what the noun is that they're modifying? Well, what we could say, here's what's kind of interesting. We say, look, we would want our rectangle to be divisible by 4 so we could take 1/4 of it. We also want our rectangle to be divisible by 5, so we could take 1/5 of it. Now, this is the beauty of having a rectangle versus just a number line. Because now what I can do is I can take the rectangle, divide it into 5 equal parts vertically, so that will give me the right number of fifths, and then 4 equal parts horizontally, because then that will give me the right number of fourths to deal with. So what do I have all together? You could count these, but isn't it rather clear that I have a 4 by 5 rectangle, which means I have 20 pieces altogether? How did I get to 20? I found a common denomination, 4 times 5. In other words, to be able to divide something by 4 and by 5, just make sure it's divisible by 20. So now what happens? 1/4 of my rectangle are these 5 pieces. And what's 3/5? This is 1/5, 2/5, 3/5. What do I have? I have 3 pieces, 4 times, that's 12 pieces. So 1/4 of the rectangle plus 3/5 of the rectangle, and notice I'm not saying what the rectangle represents, would be 17 pieces. Well, that's the right answer if the noun was pieces, but what noun is implied over here? It's the entire rectangle. Remember, we can only write that 2 numbers are equal if they modify the same noun. So without specifying what the rectangle represents, I'm still going to say whatever it represents the same. All 3 of these represent the same noun. So it's 17 pieces out of a total of how many? See, what have I actually done? I've divided the rectangle into 20 pieces, and I have taken 17 of those pieces. And by the way, later on, we're going to show how you add fractions. And some of you may recall learning it the same way I did. 5 goes into 24 times. 4 times 3 is 12. That's just 12 pieces. 4 goes into 25 times. 5 times 1 is 5. That's just 5 pieces here. sometimes students would say to me, I find it easier to do it this way than to do it the way you did. I don't want to draw this picture all the time. Well, the answer is I don't draw that picture all the time either. I do it the short way. But the difference is I understand what the short way means. Okay? So, and by the way, now that you see how fractions depend on a thorough understanding of multiplication and division of whole numbers, let's go back now. We finished the going ahead part. Let's flash back now to where we were when we just finished the arithmetic of whole numbers and point out that students, by the language of nowadays, the last I heard, is they talk about skip counting. In other words, in the same way that we talked about dividing this into 4 equal pieces with 5 slices each. How many pieces were there? There's 1 group of 5, 2 groups of 5, 3 groups of 5, 4 groups of 5. And the kids kept calling this with skip counting by 5s, just a new vocabulary term. And why is 17 not a multiple of 5? Well, you come to 17 after the 3rd multiple of 5, but before you finish the 4th multiple of 5. So a very nice way to segue from whole number arithmetic into fractions without making it look as if there was a gigantic jump is to deal in terms of rectangular arrays. Every non-zero whole number can be represented in at least one way by a rectangular array. Why do I say in at least one way? Well, the least number of tally marks you can have is 1 tally mark. And we're going to call the tally marks tiles because kids can see that better. And the tile is already what? A 1 by 1 rectangular array, and there's nothing else you can do with it. So every other whole number is going to be able to be arranged in 2 or more ways as the product of 2 numbers. Some numbers can only be expressed in 2 ways. For example, let's look at the whole number 2 in terms of a rectangular array. Suppose you have 2 tiles. What is 2? It's either 2 times 1 or it's 1 times 2. You can either have 2 rows each with 1, or you can have 1 row each with 2. In other words, you can arrange the tiles this way, vertically, or you can arrange them horizontally. It's possible that a student might say, isn't this really the same thing? Well, not as a quantity. For example, it makes a difference whether you're buying 2 pens at $1 each or 1 pen at $2 each. So in terms of the picture, we could say to a student, no, if this was the shape of a window, these 2 shapes are different. If this was a building, this is a narrow building with 2 floors. This is a wide building with only 1 floor. In other words, they're different designs. And by the way, if a number can only be arranged as a rectangular array in 2 ways, we call that number a prime number. See, 2 can be written as 2 times 1 or 1 times 2. That's all. 3 is 3 times 1 or 1 times 3. 4 is 1 times 4 or 4 times 1, but it's also 2 times 2, so we don't call that a prime number. Prime in this sense means primitive. They're the atoms of multiplication. In other words, every number that isn't a prime number can be broken down so far that it has only prime number factors. The first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Why isn't 27 a prime number? Because it's 9 times 3. Why isn't 21 a prime number? Because it's also 3 times 7. If a number is not prime and it's greater than 1, we call it a composite number. And we give one a special name. One is called a unit. Now, the point is that we can use tiles to visualize divisibility. And here's an interesting experiment. Give the students, for example, 12 tiles and have them see how many different rectangular arrays they can form using all 12 tiles. Well, they can do this by trial and error. See, if they decide to arrange the tiles in rows of 5 each, see what's going to happen? This will use up 5 tiles. This will use up 10 tiles altogether. And now you only have 12 tiles. So what happens is you can't make a rectangular array. These would be missing if you only have 12 tiles. And what that means algebraically, arithmetically, is that 5 is not a divisor of 12. it means that 5 goes into 12 2 times with a remainder of 2. So what numbers is 12 divisible by? Well, it's obviously always itself times 1. So 12 times 1 would be this long building. 1 times 12 would be this very wide building. See, and again, keep in mind, 12 items at $1 each is not the same transaction as one item for $12. So these are going to occur in pairs. You see, if you can have a 4 by 3 rectangle, you can also have a 3 by 4. In other words, in terms of commutativity, 4 times 3 equals 3 times 4, but they look different. In other words, all the numbers are going to occur in pairs, because if 6 times 2 works, 2 times 6 will also work. Well, I said they'll always work in pairs. There's one exception. What if the length and the width were equal? What if something was 4 by 4? You see, we said every time you reverse the factors, you get another arrangement. Well, look what happens with 4. You can make it as 4 times 1. You could also make it as 1 times 4. But you could also make it as 2 times 2. The difference is you say, okay, now I'll reverse the order of the factors. Well, it's still 2 times 2. In other words, the perfect squares will be the only numbers that can be arranged in an odd number of ways. In other words, you get the pairs plus the one time when the two factors are different. All the other numbers factor in an even number of ways. Now, this is where we come to how we're going to use some of this material in dealing with fractions. The product of two whole non-zero numbers can always be represented by a rectangular array or the area of a rectangle. For example, 4 times 6, we can look at that as what? 4 rows, each with 6. And you see we get the fourth multiple of 6 this way. 6, 12, 18, 24. It's also can be broken down this way, in which case it's the 6th multiple of 4. In other words, when you're counting by 4s, it's 4, 8, 12, 16, 20, 24. Okay? Now, this is all I want you to see for today's lesson. I think that's all I wanted you to do was to show you that if we take the time to get used to having the students see that sometimes, in addition to wanting to take more than an item, you might want to take a fractional part of it. And you know how many times you do that. You go into the store and say, give me a quarter pound of this. Sometimes with the price of gasoline, you don't want to fill up the tank, and you might want to only fill it up halfway or a third of the way. And don't you sometimes say at the gas station, give me $10 worth? Or sometimes you say, give me 5 gallons. In other words, those are whole numbers, but only a fractional part of what it would take to fill the whole gas tank. So anyway, let's see if you get the knack of why it's so important to understand prime numbers when you do divisibility. Okay, the first few prime numbers are 2, 3, 5, 7, and 11. Here's our practice problem for today. This is where I want you to pause the video, read the problem carefully, think about it, see if you can work it out yourself. Whether you can or you can't, when you've given yourself enough time, come back to watching the video and see my discussion of why I gave you this problem to do, okay? Well, let's look at 173. I've already told you, so you didn't have to experiment this way, that it's not divisible by 2, 3, 5, 7, or 13. Now, ordinarily, you could say what? My goodness, 173 is so big, I got to go on further and further and further and further. This is going to take me forever to see if 173 is a prime number or not. Well, if 173 isn't a prime number, it has to be divisible by a prime number. Because if it has no divisors, how can it possibly be anything but a prime number? So if it is divisible by one of these numbers, what is the smallest prime factor it can have? Well, it's not divisible by 2, 3, 5, 7, or 13. What's the next prime number? Let's see if we can figure it out logically. We'll do it the long way. 14 is 2 times 7. That doesn't work. 15 is 3 times 5. See what I'm saying? Any number is itself times 1. But to be prime, that's the only way you can represent it. See, 14 is 14 times 1 and 1 times 14, but it's also 2 times 7 and 7 times 2. 15 is 3 times 5 and 5 times 3. 16, oh, there's a lot of those for 16. It's 4 times 4, it's 2 times 8, it's 8 times 2. It's not a prime number. How about 17? 17 is a prime number. How do we know? Well, try it. It's not divisible by 2. It's not divisible by 3. I don't even have to test whether it's divisible by 5, because if it's not divisible by 2 and it's not divisible by 3, 5 has to be the smallest prime factor it could have, and 5 times 5 is already 25, so it's too big. So I know 17 is a prime number. So the next prime number is 17. However, if 17 was the smallest prime factor, the smallest the number could be would be 17 times 17. That's 289, and 289 is too big to be 173. So without any further testing, I already know that 173 is a prime number. That's going to be very, very important, because when numbers are not prime numbers, it's to our advantage, as we'll see as the course goes on, to be able to break the numbers down into prime numbers. Well, I think this was already a little bit on the long side, and I think it deserves a rest. So let me sign off for now. I'll look forward to seeing you all again for our next presentation. Until then, have fun, work hard.